Lisa is a Montrealer and did her undergrad in physics and honors physics here at McGill. And then I convinced her to stay on for grad school. So she's working primarily on hot Jupiter atmospheric characterization using the Spitzer Space Telescope, which is an infrared space telescope. But as you will hear in her presentation, she's also branched out partially due to a Teps international internship, which all of you students and trainees should do, where she went down to Caltech and collaborated with microlensing people. So anyhow, so she's going to be presenting something that is not the work that she does with me, but is really cool, and it's exoplanetary as well. All right, take it away, Lisa.
All right, thank you, Nick. Just gonna try to share my screen. Everybody sees my slides and hear me?
Yes, I can hear you.
Okay. All right, thank you, Nick, for the introduction. So as he said, today I'll talk about the Spitzer microlensing campaign and my effort in getting more precise results from this campaign. So since microlensing is intrinsically very different from other methods we use to detect and characterize planetary system, I thought I'd briefly go over the basics of this method. So microlensing, or a microlensing event, occurs when two unrelated objects, a background source and a foreground lens, come in and out of alignment along the line of sight of an observer, as illustrated on the right here. So because of general relativity, the lensing object will bend the trajectory of light coming from the background source towards the observer, as illustrated. As the two objects move into alignment, the background source will appear brighter, it will be magnified, and as they move out of alignment, the background source will then go back to its original brightness. So by seeing objects getting brighter and dimmer in the sky, you can infer the presence of massive lensing objects. I'd like to note here that there is no need to receive any flux from the lens to observe this phenomenon. All of the flux that you observe comes from the background source. And for this reason, microlensing is a great method to detect very faint and distant objects. Another advantage of microlensing is that the timescale of these events is also correlated or contains information about the mass of the lens. So not only you can detect objects without seeing them, you can also measure the mass or get mass constrained on these objects that you don't see, which is very neat. So before you actually get to getting the masses of these objects, there is something that you have to go through, which is breaking what is known as the mass distance degeneracy. So to illustrate this, I have three microlensing events that are illustrated. And at the bottom, you have an observer that is looking towards a lens that you see indicated with a circle. So the circle represents the Einstein ring, which is proportional to the mass of the lens and indicates the region of space-time that is distorted due to this lens. At the top, you have the source that is moving across this Einstein ring. Hence, the time scale, or the time that it takes to move across this ring, gives you information about the mass of the lensing object in the middle. In the second case, I have a lens that is more massive than the first one, and therefore the Einstein ring of this object will be larger, and the time scale of the event will be longer. And on the last case, on the right, you have a lensing object that is less massive, but this time it is located much closer to the observer than the two previous ones. But you can see that the timescale is very similar to the one in the middle for a more massive lens. And this is where this mass distance degeneracy comes from. You can break this degeneracy by measuring the distance of the lensing object. But recall that most of the time, you don't get any flux from the lensing object. So how do you measure the distance of an object you don't see? So analogous to parallax, there's a quantity in microlensing known as the microlens parallax. So basically, if you have a microlensing system, like the one I have on the right here, and you simultaneously observe this microlensing event from Earth and from a very distant observatory, you will then see very different things because the viewing geometry as seen from Earth and the satellite is very different. This means that the time of closest alignment and the impact parameters will be very different as seen from each observatory, resulting in two very different light curves, as you can see on the left. And this difference between the two light curves gives you basically this quantity known as the microlensing parallax, which tells you basically how far away the lens is and how far away the source is. And once you know this, then you can get the mass of the lens. Another cool thing about microlensing is that it is also sensitive, is also a method of detecting planets. So most lensing objects are actually stars that are very faint, and sometimes they are accompanied by a planet. This planet and the mass of this planet will also bend space-time and bend the trajectory of these lights, resulting in a perturbation in the light curve, as you can see on the left here. So by being able to see these anomalies in the light curve, you can infer as well the presence of a planet and get the mass of this planet. Combining everything that I just talked about, this means that if you repeat this many, many times, you can then get a distribution of planets, both spatially in the Milky Way, but also a distribution of planetary mass in the Milky Way. And this is exactly what the Spitzer microlensing campaign running since 2014 is aiming to do. So basically it starts with ground-based microlensing surveys that monitor a bunch of sources in very dense regions, like towards the galactic bulge. And out of all of the microlensing events that are detected, a handful of them are then selected for simultaneous observation with Spitzer. And note that most microlensing events last about a month or so. So this gives us enough time to be able to get these simultaneous observation. And if you repeat this enough time, then you can build a significant distribution of mass and planets and locations of planets. However, microlensing is very unpredictable. Hence, the detection rate for this method is very slow. And for this reason, since you don't have a lot of events that are detected or planets that are detected by this method, it is very crucial that you get good photometry with those observations. So far, the microlensing campaign has over 30 publications. There are much more to come. So what I'm showing here is an example of a microlensing observation with Spitzer. What we're looking at is basically an event called Ogle 2015 Bulge 0448. And right off the bat, you can see some challenges in getting really good precision photometry with this image. So the pixels are fat, some of the events are very faint. You're also looking at a very crowded field, so you get a lot of blending. And on top of that, you have all the instrumental noise that comes with the detector and the space telescope. And so here, what I'm showing is basically the light curve for the event that I showed earlier. So in blue, you can see the Ogle data. So these are the ground-based data that were obtained. And then in red are the data that is obtained with Spitzer. You can see that both of them, if you look at them from afar, there's no obvious perturbation here. They look like single lens objects, but if you look more carefully at the Spitzer data, it deviates a little bit from the single lens model. But unfortunately, in this case, this is also corresponding to the aplanetary signal. So it would be really nice to know whether this sort of like leftover systematic is due to instrumental noise that we weren't able to remove from the Spitzer data, or if it is actually astrophysical and it comes from a planet. And so, as Nick said, most of the time I work on studying hot Jupiters, and I mainly use the Spitzer Space Telescope to do that. The entire transiting and phase curve and hot Jupiter community that use Spitzer over the years have developed a bunch of decorrelation and self-calibration methods to basically extract very, very small signal from Spitzer. So we wanted to know whether we could use any of those decorrelation methods and apply them to microlensing. And it turns out we tried a bunch. A lot of them didn't work. The one that did work is pixel level decorrelation. So pixel level decorrelation stipulates that when you have an image of a source, like the one that you see on the right, then the source brightness is some arbitrary function of the intensity of each of the pixel near the centroid of your source. If the star gets brighter and there are no systematics and the centroid of the source does not change, the fractional flux recorded by each pixel should remain unchanged. But in reality, there are detector systematics, and the telescope's pointing isn't always perfect. This means that any changes in the fractional flux measured by each of these pixels is due to systematics. Therefore, you can express the light curve that you get from Spitzer observation as a combination of two things. First thing, the astrophysical signal. So what is the underlying signal that you're detecting with your detector? And then you convolute this with a noise model or a detector model, which is some arbitrary function of the fractional flux measured by each pixel. All right, so to basically prove that this is somewhat working, we, instead of going after the first event that I showed you earlier, we decided to go with an event that had full coverage that could be analyzed with Spitzer data only. And so on the right here, I have on top the raw data that is extracted from Spitzer observation. And then I fit a single lens to this and try to remove try to calibrate this data by removing some of the detector noise. And so on the second panel in the middle, this is the corrected light curve that you get. And at the bottom, you have the residual. On the right side, I do the same thing, but this time I use a binary lens model. And so this is a model where the lens is a star plus a planet. And this is the light curve that I get in the middle. If you compare the root mean square, or just RMS of the two events, you see that the model significantly prefers the binary lens model. And this is actually an event that was already published where they actually found a planetary signal, and so this is reassuring. Now, we went after the event that I showed earlier, and in this case, our model also seems to prefer the binary lens model, even though the anomaly is not as significant or as strong as the first case. And so in this case, you would end up with a planetary system with a projected separation of about 0.7 in units of Einstein ring, and then a mass ratio between the planet and the star of 0.04%. And so I still have to convert these into actual units, but it's reassuring to know that the model seems to prefer the planetary system. And so maybe this means that this is another planet that adds to this campaign. And so I think I am soon running out of time. So I'm going to go ahead and go with the summary. So what we've learned today, I have explained to you what microlensing does and how microlensing can get you a spatial and mass distribution of planets in the Milky Way. We know that high precision photometry is hard, and this is because Spitzer was not necessarily built to do this kind of work. And pixel level decorrelation can help us, or could be used out as an alternative photometry pipeline to basically fact check or verify whether there are any planets detected by the campaign. And so for the future, for those of you who don't know, Spitzer is coming towards the end of its mission. By January 2020, Spitzer will no longer take observation, but luckily in the future, WFIRST, which is the next NASA flagship mission after James Webb, will have a big microlensing component, and to some extent will be able to continue the work of Spitzer. Since this is also an infrared space-based telescope, we expect that WFIRST will share a lot of the same detector and instrumental noise as Spitzer, and so this method could also be applied to WFIRST and help in obtaining exquisite photometry. So if there are any questions, I am ready to take them.
All right, Lisa, very interesting. Yeah, so I open the floor for questions.
I have a question.
Yes, go ahead.
So this pixel level decorrelation seems like it might be, could be dependent on the size of the aperture that you choose. Like if, you know, it's a very diffuse source, where do you define the end of the signal? I don't know, maybe the pixels are very large though, so that's a negligible effect. Have you looked into the impacts of that?
Yes. So the trick here, since we're looking at a very crowded noise, we didn't want to include too many pixels because otherwise you would start to include too much flux from nearby sources. And so this is kind of like trick you have to do in balancing how much pixel you want to include into this versus how much contamination you want to include in your aperture. And so this is kind of a case by case basis. So you would have to look at the images and see how much empty fields you have around your sources to determine the size of your aperture.
All right. If there are no more questions, or if you have questions, please speak up. If not, let's thank Lisa one more time. And then we're going to go to 2 more talks from the University of Florida, of Victoria. So we're going to start with Benjamin Gerard. He's going to talk about direct imaging of habitable zone exoplanets in the next decade. And then afterwards, we're going to have William Thompson, also from the University of Victoria, who will also talk about direct imaging of exoplanets, and specifically improving our images of exoplanets using SNR optimization. So let's open the floor for Benjamin first, and then we can have William afterwards.
I don't know, maybe Christian wants to give an introduction, or should I just jump in?
Yeah,
a few words, maybe 30 seconds or something like that. Yeah, Ben has been in the University of Victoria for a couple of years. He did his master with me and now his PhD. He started doing a bit more science, analyzing data with HST and GPI, but for his PhD, he decided to move on more in instrumentation. He's been developing a new type of coronagraph and ways to do advanced focal plane wavefront sensing, so a way to sense the wavefront directly in your science detector plane. And we've been pushing this on our New Earth laboratory here at NRC and trying to validate these techniques that could open up a huge amount of contrast performance improvement over the next couple of years if we can deploy this at telescopes. So yeah, Ben, go ahead.
Okay, thanks. Can everyone hear me, and am I sharing the right screen?
Yeah, if you could start the presentation, because right now we see the viewer, the presenter's mode.
All right, swap displays. So there's the.
Great.
Okay. All right. So here's a plot from the exoplanet.eu database as of a few months ago, showing host star age on the y-axis versus exoplanet separation on the x-axis. So this is kind of selective in choosing age on the y-axis to only 3 methods that can measure the age of the host star. So different symbols are different detection methods here, and then mass is in color. So I like to show this age parameter instead of mass on the y-axis because it nicely separates directly image planets. I don't know if my mouse is visible. I'll just describe verbally. And I think that this is a useful way to show that direct imaging is complementary to other methods. We're looking at the moment at planets on wide separations and at young ages, which is a unique part of this parameter space, so we can study giant planet formation. And it also shows that there's areas at closer separations and also at older ages that we're looking towards in the future to fill in when we can improve the technology to detect those planets. And another useful way of looking at this plot is now showing only the remaining colored points are those exoplanets which have a measured spectrum. And you'll notice, going back and forth between the two, that all of the directly imaged planets remain there, and there are only a handful of now transit spectroscopy planets that remain in the upper left here. Again, just showing that these are complementary methods, but that what's nice about direct imaging is that at least now with current instruments, when you can detect an image, you can also detect a spectrum. So I think moving forward, a reason why this is main focus of a lot of future missions is that we want to detect habitable exoplanets. So ultimately we want a spectrum like this. So this is a near-infrared spectrum of Earth. And as opposed to just detecting a single point source from a planet light, really to agree that a planet is habitable rather than just detecting a planet in the habitable zone, there will be a number of different molecular lines or bands or features that will need to be detected for people to agree on that. As you can see, there's not just one molecule that indicates habitability in Earth's atmosphere. So that's a nice benefit of direct imaging, is that we'll be inherently getting a spectrum through the technique moving forward. So in terms of ways we can do a habitable exoplanet detection with direct imaging, there's not one. We could look at the light reflected by the planet that's emitted by the star, or we can look at the light emitted by the planet from thermal emission. And there's a lot of different ways these two approaches are thought about being done. In thermal emission, it's easiest to do that at 10 microns because Earth is the brightest at that wavelength. And so the planet to star contrast ratio is the easiest to reach with current instruments. Whereas with reflected light, that is fainter for an Earth analog in the visible, and we really need to go to space telescopes to do that. But for the closer habitable zones around M stars, that planet is much closer to the star, and so it's much brighter in reflected light than the FGK habitable zone equivalent planets. And so with that, we can potentially reach on extremely large telescopes in the next decade, plus or minus 50% of a decade. So the rest, for the rest of my talk, I'll focus only on that. Each one of these subjects would be an individual talk. So M star habitable zones is really where extremely large 30-meter class telescopes will be targeting to try and image habitable exoplanets. So the resolution limit, though, for a 30-meter telescope in the near infrared is about 10 or 11 milliarc seconds. And these habitable zones, here's the sort of 10 best candidates of nearby M stars, are at a separation of close to that limit, 1 to 2 lambda over d. So this is really reaching the limits of even the largest 30-meter class telescopes. although in principle reachable, whereas the contrast, that's where I'm gonna pause. You can sort of, maybe if people in the field know current instruments now, you can see there's a gap, but I'll come back to that and motivate why we may be able to reach these contrasts later when we improve the instrumentation. So here's a sort of conceptual block diagram of a high contrast imaging instrument. You need to have the resolution to reach that diffraction limit. So on ground-based telescopes, that really means adaptive optics, which includes a wavefront sensor to measure the turbulence in the atmosphere and a deformable mirror to correct for that turbulence, and a control system linking those two components and updating as the atmosphere is changing. And then you need ways of correcting or improving contrast. Even with a perfect adaptive optics system, you won't reach a very deep contrast. So we use coronagraph and various speckle subtraction techniques. NCPA, non-common path aberration, that's all of the static or quasi-static aberrations in this path that isn't measured by the wavefront sensor. And so we need some other way of correcting those aberrations to improve in contrast. So just to give you an idea of what I'm talking about by speckle correction, this is a processed image of the lowest mass directly imaged planet on sort of solar system scales to date, 51 Eridani b, where all of the hour-long observing sequence is collapsed into a single image. So it's fairly easy to see the planet there, but this is what a single raw image looks like at a single wavelength and single time. The planet is buried in this speckle noise. And so this is what we're fighting to try and improve the contrast. And this noise is, as I mentioned before, quasi-static and in parts dynamic. So this is just frames across the hour observing sequence, where if you look at some region of the image, you can try and imagine, subtract one frame at one time from another frame at another time, and you're not going to get zero. There'll be some residual because of this quasi-static speckle evolution. So you see that everywhere. Also, there's a faster evolution, particularly in the direction of the wind. This is because the adaptive optics system doesn't make a perfect correction of the atmospheric turbulence as well. So these effects are both present, and we have to improve them if we want to go deeper in contrast. And if we don't, this is an important point to make on extremely large telescopes, this solid curve on the right is contrast, so normalized instrument sensitivity, or the noise floor normalized to the brightness of the star, as a function of separation. And it's basically going to move to the left. We'll have a larger telescope, so we'll have better resolution, but it's not going to get deeper because these quasi-static aberrations are not going to go away. They'll be roughly the same order of magnitude, and with the same techniques, we won't be able to correct any deeper. So the brightest tip of the iceberg habitable zone M-star exoplanet is Proxima Centauri b, and now you can see the gap that I was talking about earlier. We're a few orders of magnitude off from where we would need to be if we wanted to detect an exoplanet. So the way I've been pushing to develop to bridge that gap is a method called focal plane wavefront sensing, modifying the diagram I showed before. The science camera turns into a wavefront sensor, basically. So you have you can imagine a second control loop feeding back to the same deformable mirror, and basically doing the measurement with the science camera. That's the plane where you want to measure all the speckles that are forming in the image, and this is thought to be the path forward. One of the issues, though, is that this technique has generally been developed for space telescopes. So it takes a while to converge, and it doesn't work on large amounts of aberration. So you need to close the adaptive optics loop first, and then you need a very stable system. So I've been pushing to develop a method to make this work on ground-based telescopes, where you have a lot of variation on dynamic and quasi-static timescales. I've been working on this for most of my PhD now, so I have a lot of different papers on this topic. I'll just describe the basic principle here. So it uses this concept called the self-congruent camera, which is uses the general aspect of a coronagraph. So here's the intermediate focal plane where you block the core light of the star, and then in the pupil plane downstream of that, the dotted blue line is the remapped pupil of the telescope, and now there's a bunch of light diffracted outside of that pupil. This is why you use a Leo stop, a washer-shaped component, to block that diffracted light and improve the contrast in the final image. But in a self-congruent camera, you have a pinhole in that Leo stop that transmits a small amount of that off-axis light, and then focused onto a detector, in addition to the speckle pattern, records these fringes that you see in the vertical direction, and that allows you to measure the full electric field of this speckle pattern and correct with a deformable mirror or with post-processing. One of the problems with this approach, though, is that you can see there's much less light in this pinhole than all of the light in the pupil, and I've had to unphysically enhance that intensity distribution by a factor of 1,000,000 in these right two images, so you can see the fringes by eye. But what I proposed is instead a new coronagraphic mask designed to physically enhance the light in that pinhole and enable detecting fringes on millisecond timescales to do this speckle subtraction, freezing residual atmospheric turbulence, and quasi-static aberration. And by subtracting these millisecond exposures, that basically allows you to get a subtracted image where the residuals are in principle random. You're now limited by just photon noise in a millisecond image, so that's not a very deep improvement. But when you stack those images as a function of time, because those residuals are random, this is contrast as a function of time at a single separation, you can in principle continually improve down to deeper limits than we can reach with current instruments, whereas the blue curve we're sort of saturating after a second in raw contrast because of these quasi-static speckles that we're not subtracting in the raw images. So this gives you an idea after 30 seconds, if we look at the blue curve versus the orange curve, you can see a planet that can be detected. This is all in simulation, just illustrating the principle of the technique. But in principle, if we extrapolate this for the hour observing sequence of 51 Eridani b, where I showed before, we could improve by a factor of 100, which is maybe about the gap that we need to reach to detect habitable planets on ELTs. So there's a simulation with this technique implemented of a detection of Proxima Centauri b in only about 30 minutes, because this is not limited by quasi-static speckles anymore. It's just limited by photon noise, and you can detect a lot of light on a 30-meter telescope, so you can reach these limits very quickly. All right, probably over time already, so I'll just leave it at there. In summary, we cannot, with current technology, detect habitable exoplanets on ELTs, but there's future improvements being pioneered, one of which we're doing here at HAA that could in principle enable this.
All right, Benjamin, thank you so much. Are there any questions? If not, I have one, but maybe I open the floor for the other ones first. Okay, so maybe I start. So when you do these simulations, those are, I guess, for example, if you simulate, I guess you're simulating exactly when. Can you go up one slide? When you simulate, another slide. Another slide. If you simulate what falls onto the in this case on the detector, is this all time resolved calculations, or how do you do this? So are you basically at like 1 kilohertz or several kilohertz simulating what would fall on the detector?
That's right. So, I'm simulating a moving atmosphere, just like you would in an adaptive optics simulation. The evolution of those speckles on millisecond timescales. We're not yet simulating the quasi-static effects, and that's not well, at least we don't think there's evolution on those timescales, but that's still a more unknown regime. We don't really have a lot of measurements, at least wavefront sensor measurements on that information. So yeah, it's sort of, I hesitate to go into a lot of confidence that where I say we can gain by a factor of 100 relative to current instruments, because I think there's still a lot of work that we need to do to understand why we're reaching the limits that we are on current instruments and implementing that physics into these simulations. I would say there are various aspects, like you said, of atmospheric residuals being included, but I think there's still a lot of unknown factors.
So I guess what I'm understanding is, so your simulations, they do have like the variations that are at the kilohertz or at the kilohertz level, but they don't necessarily include the variations that are coming over the course of 30 minutes or something?
Yeah, unknown. Could be over the course of 1 minute or 1 second. There's definitely a full power spectrum of quasi-static aberrations, but yeah, the relative strength of those on different timescales, yeah, it's unknown at this point.
Maybe I could clarify. I think John was asking, in your simulation, you did add 2 components. One was the atmosphere moving, but you also had the quasi-static speckle. You just consider these fully static for that simulation.
That's right. So I would call those static speckles and not quasi-static speckles, at least as they've been simulated.
So basically at kilohertz speed, the technique can still detect a quasi-static speckle that you would only see after 1 or 2 seconds, but the technique that Ben is working on can sense these aberrations and correct them as we go.
Yeah, so I would say in this image in the upper right, atmospheric residuals are about speckles, or maybe 75% of the speckles that you see, and static speckles are about 25%.
But even the static speckles, they are basically fluctuating at the high frequency level?
Yeah, good point. I mean, they interfere with the atmospheric speckles, so yes, they are.
I guess this final question. So you would be able to make a video of that detector plane, like that would show how the speckles move over the course of 1 second, for example. Or
definitely, yes. Yeah, I could pull up another slide and show that video, but I think that's pretty good.
Okay. Yeah, I might actually follow up on you with you on this, because I'm also interested by this. Okay. Are there any other questions? So if not, then I would say we go to the next speaker. And Christian, how about you also introduce the third speaker then?
Yeah, sure, no problem. So actually, just for finish, Ben, he actually did 2 internships to complement what Nick was saying for his students. He did one at Honeywell, one at Paris as an international one. And Ben is also defending on spring 2020, so he's finishing in a few months. So next speaker is going to be William Thompson. He started at UVic as a master's student a year ago. He's actually not part of Teps. He's part of NTCO, which is another CREATE that's being led at UVic, but he's an unfunded Teps trainee. He's just finishing an internship at NUVU, and we're going to move into the PhD early 2020. So he's working on two main projects. One is what it was described in the email, which is supercomputer-based post-processing for imaging exoplanets. But after spending a 2-day trying to make a talk that would be easy to understand, he kind of gave up. So he's going to be talking about his second project. So developing a new concept to use space-based laser for imaging habitable zone rocky planets around a near star using ELT. So we thought that would be a better slides and a better subject to discuss at this meeting. Go ahead, William.
Hi, Christian. Thanks for the introduction. And also, thank you, Ben, for all of that great background on direct imaging. So that means I can skip a slide or two. So this is a concept that was first envisaged, I think, by Christian. And then we've been working on a little bit on over the last year or so. And we presented at AO for ELT in the spring. So Ben already presented a good motivation for direct imaging, but I would like to also add that I think time series photometry is really interesting, the ability to watch the planet rotate and evolve over time. So here's a simulated image that Christian made of a 10 micron image of our solar system if it were seen from Alpha Cent. So this is the sort of image we might dream of one day getting. So Ben already described the challenges in direct imaging. Very high resolution and very high contrast are required. So the contrast for an Earth-sized planet in reflected light is around 10 to the 10 times dimmer than its star. And that has to be achieved within a few lambda over d separation from a star. So current plans on how this could be done often involve going to space with very large telescopes. So for example, HabEx or LUVOIR, which are in the multi-billion-dollar price tags, and very exciting. But we're wondering, what if there's a way we can shift some of this R&D effort to the ground? So directly imaging exoplanets already requires state-of-the-art adaptive optics systems. So I think we've all seen these diagrams before, but as a quick recap, they measure the incoming distorted wavefront from the star, apply an opposite correction. So if we had a perfect adaptive optics system, we would have one that is that completely mitigates lag, mitigates very high order aberrations, and also accounts for chromatic effects between the guiding and science wavelengths. So taken to the extreme, we would like to correct the wavefront errors before a single aberrated photon arrives from the star to pollute the image. So it follows that if we're going to correct the atmosphere before a single aberrated photon arrives, that means we need a brighter calibration star source than the star itself. So that brings to mind laser guide stars. Sodium laser guide stars are already common. They work by exciting a layer of sodium in the upper atmosphere to produce an artificial guide star. Here's a picture of two lasers going at Keck. But laser guide stars do have several weaknesses for this application. So for one, I'm told that there's difficulties in making them sufficiently bright. Second, they suffer from spot elongation because they're at a sort of finite height and launched from the side of the telescope. There's sort of a viewing angle effect. They also suffer from something called the cone effect. So the laser being at a finite height doesn't probe the full content of the atmosphere that the star is shining through. And also, it's always at the same wavelength, which is the one that's used to excite the sodium. So it's often not in the science band. So a possible solution could be orbital guide beacons. For high-value targets like Alpha Cent, small satellites could be equipped with lasers or perhaps retroreflectors and placed into orbit. So they would be very bright. They wouldn't suffer from spot elongation or the cone effect because they'd be so far away from the observatory. They would be usable at any convenient wavelengths. And they would also, as a bonus, act as a close to ideal photometric calibration source. So here are some results from some very basic simulations looking at how we could place these satellites. So as a requirement to keep the mission somewhat in the realm of feasibility, we'd want to not have to expend propellant to keep the satellite in view of the target. And we'd want the satellite to stay in view of the target for long enough to acquire images. There's some delay for an AO loop to close and to stabilize, so we don't want to have to do this too often if there's multiple satellites coming into view, for example. So it also must return to the same target with some regular period so that we can undertake observations multiple times. So to do this, we need to minimize the relative velocity between the observatory and the satellite. And highly eccentric orbits are one of the best ways to do this. So a highly eccentric orbit sort of stalls out at its apogee So if we can place this apogee between the observatory and the target, that will give us the longest possible observing time. So it's also nice if we can choose an orbital period that is about a multiple of one sidereal day. So here is a simulation of a target at zero declination seen from an observatory at the equator, and some possible orbits with different periods. So each of the different colors is a different period, and you can see in the legend on the left how long they last. This one on the right would be for 10 days, so it would come to the target every 10 days. The vertical axis is how long it would remain within that 35 arcsecond field of view. And on the horizontal axis, I've varied the eccentricity. So there's an optimal eccentricity for every period, essentially. So already this is actually interesting because it seems like it's maybe somewhat within the realm of feasibility, because it could stay on target for up to 200 minutes, which I thought was quite surprising. And if I take a look at that 200-minute conjunction, this is what it would look like seen from the observatory on the ground. So the black line with dots shows the motion of the satellite into and out of the field of view. So it approaches fairly quickly, and then it slows right down over the target for over 2 hours, and then eventually moves out. So for a more realistic target, and one that's more challenging, here is Alpha Cent seen from Gemini South. Here you notice the conjunction duration for a 10-day orbit has gone down to 50 minutes, but that's still, I think, long enough to be interesting. If I plot this, we get this really fun-looking orbit. It sort of exhibits retrograde motion just because of the inclination. So the satellite you would see approach from the left and then loop around the target during your observation and then move out to the right. It could also be interesting if we could launch a constellation of these laser guide stars so that we could perform tomographic reconstruction to reduce the effects of anisoplanetism. So here's a constellation that we imagined moving past a target, the declination of 10 degrees, seen from Mauna Kea. So now a few words on how bright they could be. So if we assume a 10-centimeter launch telescope on the satellite and a 20-watt output laser and fine pointing capabilities, which we might need a laser uplink from the observatory to enable. Or alternatively, we consider a 10-centimeter retroreflector reflecting light from a 2-kilowatt output laser launched from a 10-meter telescope on the ground. Really stretching feasibility, I know, but to illustrate the point. So here is apparent magnitude versus apogee distance. So the orbits we were looking at on the previous slides were near the right edge of this plot at about 400,000 kilometers, which is near the moon. And we still see that they are far brighter than the brightest star in the sky. So especially with the orbital lasers, they're a good fraction of the way towards being as bright as the full moon. So obviously this would eliminate most of the issues with sensitivity at the wavefront sensor detector. So I'm sure many of you have imagined some challenges with this approach. So high accuracy orbital positioning would be required. Fine pointing capabilities would be required on the satellite. The satellite would also be moving in and out of radiation belts, so it's a challenging radiation environment. Flipping to the ground side, there would be a ton of R&D necessary. You'd need to use a very high density deformable mirror to actually do anything useful with this signal. We would need moving guide star pickoff mirrors to follow the satellites as they move through the field of view. And on-axis non-common path aberrations are still a challenge. So in terms of existing concepts, people have imagined putting things near the moon with lasers before. But more realistically, laser pulses from the Calypso satellite have been used for photometric calibration from low Earth orbit. And there's a related concept called ORCAS for a repositionable laser guide beacon, which wouldn't be as bright. So we've submitted a pre-proposal to CSA for a possible lunar payload to sort of piggyback on the contribution to the Artemis mission. And Kate Jackson, postdoc at NRC, is undertaking some more advanced AO simulations to see what the new limits would be once you take away the brightness of the star as the limit for an AO system. And with that, I will go to my summary slide. So with orbital guide beacons, we could have a very bright source, stay near the target for up to 200 minutes. Thank you very much. Are there any questions?
And we can see it's lunchtime at Nuvu. We can hear that.
Sorry about that, open office.
Yeah.
Okay, I'll ask a question if no one else has any. So normally in, I think with a sodium laser guide star, other than just pointing, you have to track the focus of the wavefront sensor. So it's like it's on a stage and it's moving throughout the whole. I don't know if that's because this is much further away, but just across the orbital path, as opposed to just pointing mirrors, would you have to, you guys thought about, you would have to have the wavefront sensor on similarly tracking focus?
We haven't thought too much about it, but my guess is that we wouldn't, because they would already be about as far away as the moon.
Yeah,
so I think even for a 30-meter telescope, that would be effectively infinity. I'm not sure about that, but in the very least, the distance would be entirely predictable, and so you could set that in advance.
Mm-hmm.
You wouldn't need to track it. It's a good question.
We need more advanced simulation at some point. We currently, William is working on the orbital solution, but once we have something that's good enough, we'll move on to more detailed advanced simulation. Any other questions for William? I think we lost Bjorn. Okay, so if no, I think that's all for today. Nick, okay, so I guess we're all done. So thank you very much, everyone, and see you at the next Teps meeting. See you.
Thanks. Bye-bye.